Hello everyone. So today we are going to start a new chapter on the classical plate theory. So the plan will be exactly the same as we had followed in our previous chapter, that is on beam theory. So first of all, we are going to develop a theory for this plate, and I am going to discuss a bit on this geometry in a while. So just to get back to the plan, we are going to discuss it along the same line as the beam theory. Okay, so first of all, we're going to develop a theory for this plate, which will be simply taking into account mostly the bending. But later on, we are going to develop a modified theory uh, completely separately from this chapter, and that will be a separate chapter called the von Karman plate theory, where we'll be addressing the buckling of plates. So earlier in the previous chapter, what we had in one single chapter, both the bending and the buckling of beams. In this chapter, we are going to consider only the bending of plates, and you will see that there will be uh, a few complications as far as the development of the theory is concerned, but will rise up to the challenges and proceed. Now, regarding the geometry, you note that I have drawn a fairly general kind of plate here. I have also denoted the thickness by this h. It is such that this top surface here is at z is equal to minus h by 2, and this bottom surface is at z equal to plus h by 2, because you note that the z is pointed downward. Okay, but very important to note is that for this classical plate theory to hold, the theory that we are going to develop, for that to hold, this h must be very small compared to the lateral dimensions of this plate. Lateral dimensions means the extents that this plate has along the x direction and the y direction. So that h must be much smaller than those dimensions along the x and y directions. Okay. There will be a few other simplifying assumptions that we're going to use, but we'll see that as we go along. So just like as in the bending of beams, we are first going to start out with the kinematical hypothesis. The spirit is the same, and the only thing that we really have to worry about here is taking care of the extra dimension involved. So back in beam theory, we were mostly dealing with this x direction and the z direction. The bending was taking place in the z direction, but here additionally we have this extra dimension y. So that brings in a few more challenges. Okay, so what we are going to say is that this u will be described by this. Okay, so please note that when I write this, behind it are the exact same kind of discussions which are present in the back when we were discussing beams. So I strongly advise you, if you don't remember those, or if you have not seen those, to first go and take a look at the justification behind these kinds of terms. Okay, how this is emerging. Now back in beam theory, we had taken this v, the displacement along the y direction, to be 0, but that is no longer the case. So we will have a stretching variable vs, just like we have a stretching variable us along the x direction. We have a stretching variable now along the y direction, and we also have this term. Okay, so whatever is happening along the x direction, a similar kind of thing is happening in the y direction also. Okay, now regarding the z direction, it is almost exactly the same as in beam theory, with the only difference, but very important difference, is that in beam theory, the w, the displacement in the z direction, was only a function of x. It was a pure function of x, but now here in classical plate theory, this w is a function both of x and y. That is very, very important to note. Now, these are uh, the simplifying assumptions regarding the nature of the displacements that we start out with, and based on this, we should be able to write down using the strain displacement relations, the linear strain displacement relations which we are all familiar with, uh, to write down the various components of the strain expressions. So epsilon xx is del u del x, that gives us these two terms. In a similar fashion, epsilon yy, that is del v del y, that gives us del vs del y minus z del square w del y square. Next, for epsilon zz, we have del w del z, and please note that w being a pure function of x and y, not being dependent on z, this del w del z gives us 0. Next, for epsilon xy, we have half del u del y plus del v del x, and that will give us half del us del y. So looking at this, minus z del square w del y del x plus half del vs del x minus z del square w del x del y. So overall, what we are going to end up with here clubbing these two terms together with the half coefficient in front, and you please note that this term here and this term here, they are the same terms because we don't care about the order of the partial derivatives, and what we end up with here is this thing. All right, next for epsilon yz, we have half del v del z plus del w del y. Now before I proceed any further, I wish to make it absolutely clear that this us and this vs here, they are functions of both x and y. Okay, so please note that us and vs, they are functions of x and y. Okay, so just like w is a function of x and y, so also us and vs. Otherwise, this term, this del us del y term would have been 0. Okay, but it is not. So we keep it. So getting back to this epsilon yz, what we are going to end up with here is that you please note that since this vs is a pure function of x and y, and we have vs here, but what we need to do here is this del vs del z, and that is going to be 0. Okay, so del vs del z minus, again from this term, only this z is going to be differentiated out. This w is a pure function of x and y, so that has no business with this differentiation with respect to z, and we have this. And this del w del y, that just gives us this. Okay, so overall, since this is 0, what we have is that this is 0. And finally, for epsilon zx, what we are going to have is del w del x plus del u del z. So in a manner similar to this epsilon yz, what we are going to end up with here is this del w del x half. That doesn't change. From the del u del z term, I'll have del us del z minus del w del x, and that eventually gives me 0. Right. So you see, as far as the non-zero terms are concerned, what I have here is this epsilon xx is non-zero, epsilon yy is non-zero, epsilon xy is non-zero. The other three terms, epsilon zz, epsilon yz, and epsilon zx are 0. Okay, so there is a certain simplification already emerging out of this kinematical hypothesis. Okay, next, let's see what about the stress terms, because you note that just after this we are going to utilize the principle of virtual work to write down the various terms involving both the stresses and the strains. So there we'll need the expressions for the stresses. So let's see what happens to this stress. Now first of all, you note what happens to the case of the sigma zz, because it's a very special thing, and a simplifying assumption will be involved there. So we are going to use the linear elastic isotropic behavior, or so that kind of material we are going to use. So we have this relationship, the well-known relationship from the generalized Hooke's law. So already in the previous page we have seen that this is 0. So what this is giving us is sigma zz is equal to nu sigma xx plus sigma yy. Now in general, this sigma xx and sigma yy are not going to be 0, which means that this sigma zz is certainly not going to be 0 also. However, this is where so this sigma zz is not 0, okay, because this is not 0, this is not 0 in general. But, and this is a very important but, we forcibly, just to make our life easier, we forcibly assume sigma zz is equal to 0 despite what we see in the above line. That is very, very important. Okay, so this is a very key step in the development of our theory. There are certain justifications and there are certain arguments against it, which helps us to go forward and develop more advanced theories. Of course, we are not going to go into those, but it is important to understand that this is a forcible assumption. There are certain justifications, there are certain like very strong arguments against using such things. But anyway, we'll proceed. And there is a value to learning this classical plate theory. Okay. All right. Now, once we have this, let us go to this expression for epsilon xx is equal to this thing. Again, using the generalized Hooke's law expressions. So now we have assumed the sigma zz is 0. So this is 1 by e sigma xx minus nu sigma yy. And in a similar fashion, the epsilon yy, that is going to give us this, again sigma zz being 0, what we end up with here is this sigma yy minus nu sigma xx. So this will be familiar with everyone who has already studied the cases of plane stress and plane strain. Now what we want to obtain here is the expressions of sigma xx and sigma yy in terms of epsilon xx and epsilon yy. And if I do those simplifications, okay, if I do those simplifications, from what I get from here is that sigma xx is equal to, I'm not going through the intermediate steps here, that's just basic algebra. I obtain this for sigma xx and this for sigma yy. Okay, so now I'm more or less ready with the key expressions which I need in order to develop the theory of classical plates using or starting on from the principle of virtual work. So let me go towards that. Now we proceed using the principle of virtual work. So just like before, we do not consider the body force terms, which just start out with this expression, with the volume integral on the left and the area integral on the right. So this is the general thing, except that I have not considered the body force terms. So first of all, what I'll do is I'll consider this left hand side term, and here you please note that this is I mean, these kinds of repeated indices here, they represent the summation. And if I just write this out for the case under consideration, for the plate under consideration, then this volume integral, that can be written in this fashion. So we have this area integral. So that area integral will be over the xy domain, and I'll also have an integration with respect to z, and that integration will be from minus h by 2 to h by 2. Because if I just go back a little bit and refer to this diagram, you please note that this origin, despite what it may look like, it is actually placed at the center surface of this plate. It is not placed, this origin is not at the top surface. Okay, so probably it would have been better if I had drawn these this y direction and this x direction, these two coordinate axes as hidden lines. That would have probably made the diagram a bit more clear. But anyway, this origin is at the mid height or the mid surface of this plate. So as I had mentioned, this top surface is at z equal to minus h by 2. The bottom surface is at z equal to plus h by 2. Okay. Now, when I expand this term, what I will obtain is sigma xx delta epsilon xx plus sigma yy delta epsilon yy plus, and here I will obtain two terms, so sigma xy delta epsilon xy plus sigma yx delta epsilon yx. But we know that they are the same things, so what we are going to end up with here is twice of sigma xy delta epsilon xy. So the first integration is with respect to z, and the second integration is over the entire area covering the xy domain. All right. So what we're going to do next is to substitute this expression of epsilon xx, epsilon yy, and epsilon xy. There will be a little bit of a temptation right away to also utilize the expressions for the sigma xx, sigma yy, and the sigma xy, because we have managed to express them in terms of the epsilon xx and epsilon yy. But right away we will resist that temptation and see what it gives us. Okay. All right, so proceeding. Let's take a quick look at the expression for this epsilon xx. So what we have here is this thing, and at the same time let me take a look at this thing also. So once we do the first variation over that, what we are going to end up with is partial derivative of the first variation of this stretching variable with respect to x, partial derivative with respect to x, minus z del square delta w del x square, right? I'll separate out the various integrations. In a similar fashion to the first term, we'll have del delta vs del y minus z del square delta w del y square dz dA. And for the last term, I take the twice out of the integrations. Let me take a look at the expression of epsilon xy. The epsilon xy has these things. So so what I'm going to do here is to take the half out, and then I'll have del delta us del y plus del delta vs del x minus twice of z del square delta w del x del y. This twice is coming because you can just quickly see over here that I did not have this twice here, but here I'm taking the half common over all the terms, so that brings in the twice. Okay. All right. Now you see, in each of these terms, wherever w is appearing, it is not at all multiplied. So none of these terms, this term, this term, this term, it is not at all multiplied, meaning it is not at all coupled with either the us or the vs. And that is good news for us in exactly the same way it was good news for us back in beam theory, where such kind of absence of any coupled terms indicated that physically the stretching and the bending were completely decoupled, and we had seen that. Okay, it was as if we were simultaneously considering two separate problems, the stretching problem and the bending problem. And here also, because our intention is to address primarily the bending, so and because we are seeing very nicely that the stretching variables and the bending variables, that is the us vs variables are decoupled from the w variable, therefore what we are going to do is from now on we are going to concentrate only on the bending variables. Okay, so henceforth we are going to consider only the bending terms. Meaning that we are only going to consider the terms involving the w. Okay, so we are going to look at this term, we are going to look at this term, and we are going to look at this term. And you will see that even while making this kind of a simplification or a reduced form of analysis, we are still going to have to deal with quite complicated looking terms. Okay, now let us not forget that in the previous step, the sigma xx, sigma yy, and the sigma xy had been left unsubstituted. Okay, so when I say unsubstituted, I mean that I have not expressed this in terms of the epsilon xx, epsilon yy, and this epsilon xy here, and certainly not involving the us, vs, and the w. Okay, so do we need to do that right away? Answer is no. we are not going to do that even now. Rather, we are going to do it in a slightly different fashion, which will perhaps give us a better insight into the mechanics uh, of the problem. Okay, so what we are going to say is this. Okay, let me go to the new page here. We are going to define a few terms. It's not something new to us, but it will help us to proceed. Okay, it will also reduce the well, kind of reduce the amount of uh, writing that would be otherwise involved. So this mx is the bending moment. Now that is defined as minus h by 2 to h by 2 sigma xx z dz. Okay, so what we are saying here is uh, if you look back at or maybe just look at a uh, so let me go back to this figure. Okay, so uh, if you consider a cut section like this over here, I don't want to spoil this diagram. If you take a cut section over here, then uh, uh, the kind of figure that you would be looking at, uh, so if you look at it from the into the xz plane, it is going to look like this. Okay, our plate, this jagged line means that there is more of the plate here, which I'm not drawing. This is the x direction, this is the z direction, and out of the plane of the screen would be our y direction. Now at this cut exposed surface, this vertical one, we are going to see a distribution of sigma z, sigma xx. Okay, so this sigma xx, when it is multiplied by the z and integrated over the entire height from minus h by 2 to h by 2, again note that we are integrating from the top surface to the bottom surface in the direction of the positive z. So the entity that we are ending up with as a result of this integration is uh, this mx. Okay, now you can probably think of considering some kind of thickness into it, but it is I mean our subsequent analysis will be much easier if we just define it in this fashion. Okay, so you think about it in the and it'll strike you, and please hold on till we actually go into the simplification or of the subsequent analysis. Okay, so in a similar fashion we define this. Okay, and we also define this. So I strongly encourage you to try to uh, interpret these terms, especially this one, the sigma xy, the term involving the sigma xy. Now, uh, if we go back to the previous step here, okay, and look at it here, so we have the sigma xx multiplied by the z, and then we have this integration with respect to dz. So that will give us the mx term that we have just now defined. Similarly, the sigma yy multiplied by the z integrated with respect to the dz or with respect to z, that is going to give us the my term, and finally this sigma xy multiplied with this z then integrate over this twice z, that is going to give us the mxy term. Okay, so and we are going to neglect all this us vs business. So if we use this, what we are going to end up with is the LHS, and when I write the LHS, I mean the LHS covering only the bending terms, and that is going to give me minus mx del square w del x square dA. Please note that I have also implicitly used the fact that this term here, this del square delta w del x square, that term is independent of z. Okay, because this w is a pure function of only x and y. Similarly, this term is a constant with respect to this z, so it is independent of z, and similarly this w, this term here also is independent of z. So we are taking this term, and this term out of the integration with respect to z. Okay, so this is integration over the area A. Within this mx is subsumed the integration with respect to z. In a similar fashion, we'll have this thing, and then we'll have this mxy term integration with respect to A. But let us not forget that just take a look here, that although this half cancels with this 2, but we still have a 2 outside. Okay, so when we are writing that mxy, this 2 has to be taken care of. Okay, so we have to write this with a 2. All right, now we are going to make a number of algebraic, or we are going to write down a number of steps involving some algebraic and calculus manipulations, and we'll do that from the next video onwards. And believe it or not, even though there will be a proliferation of terms, it will be almost hard to keep track of what is going on, but you'll see that at the end we will be able to arrive at a step which will enable us to write down clearly the governing equations and the boundary conditions, much in the same way that we have been doing till now, especially quite a number of times that we have done in the beam theory. So on that note, I will end this video. Thank you very much.